In this video, I encourage you to do just a quick review of some of the concepts of a linear transform, and specifically here, if we have a linear transform from a vector space V to a vector space W, what's the name for all the input vectors that are mapped to the zero vector? So imagine we have our set V, and we have our set W, and between them there's a linear transform. Let's make that a different color just for fun. If we pick out specifically the zero vector here, in the output space, what is the name for all the points that map to that zero vector? You can just pause for 1 second or pick it out. Hopefully you said yes, the kernel, or sometimes it's called the null space of that transform L. And the null just comes from things that map to zero or nothing. So in that sense, it's the null space. Next up, that kernel of a linear mapping is which of these four properties here? Pause if you like, and then we'll go to the answer. Well, there's a hint on the previous slide, which was that the kernel has to be some property of the input space, so it cannot be anything about the output space. We already know from our configuration here that the zero vector is in the output space, and it's the zero vector. That's the only thing associated with the output space and the kernel. Everything in the input space is what we're talking about that maps to zero, and it's not just some subset. I mean, it is a subset, but more importantly, or more relevantly, it's specifically a vector subspace of the input space V. And that means we have all the nice properties of vector spaces. So the kernel of L, the set of points here, the set of vectors, is closed under addition. It is closed under scalar multiplication. It has a dimension, it has a basis, it has, all these things that we associate with vector subspaces. The kernel of L has all of those. Next up, we're going to look at a complementary subset related to the transform L, but it will be this time more on the output side.